Estimating the elevation of the snow line before and after a storm in Google Earth Engine. So first, the snow line is defined as the loose boundary between high elevation snowfall and low elevation rainfall. On the east side of the Sierra, the rain shadow side, the snow line might look something like this photo of Ruby Lake, taken by my friend Jade. It can be highly variable and hard to define. It is not a sharp boundary, as frozen, partially melted, and liquid precipitation may coexist. In other areas of the world, the snow line is easily distinguishable. The snow line is a fundamental aspect of mountain weather and climate, and the precise location at which the snow line is intersecting topography is important for several reasons. The snow line is central in determining the navigability of mountain roadways following a storm, the risk of avalanches and landslides, as wet snow is more dangerous, and the quality of mountain recreation. The snow line regulates the effects of storms on mountain stream flow. Snow is stored on the ground where it acts as a natural reservoir, whereas rainfall produces runoff much more quickly, which can potentially lead to flooding. An extreme example of a rain-on-snow event is the 1997 Merced River flood over New Year's, which stranded 2,100 visitors and caused an estimated $178 million in property damage to Yosemite Park. Snow is a crucial water resource for many communities around the world, including the western United States. Changes of just a few hundred meters in snowline elevation will have major impacts. In a paper by Justin Minder of the University of Washington, he modeled that a 200-meter rise in the average snowline elevation associated with global warming will decrease snowpack accumulation in the Cascade Mountains by about 15 to 18%. In terms of reservoir management, water managers need to know whether it's snowing or raining. In California, around 75% of our water is used in agriculture. As mentioned previously, snow acts as a natural reservoir. But when we are irrigating our plants, snow is usually not present or it is melting. It is important that we accurately forecast and manage our water resources, the primary source being mountainous precipitation. Proper estimation of the snowline will improve our forecasting, and the remote sensing of the snowline will validate models that already estimate it. In order to estimate the elevation of the snowline before and after a storm, first I had to find a good storm candidate. The ideal storm must be bracketed by Landsat 8 flybys, so I have imagery to work with. It should have a little to no cloud cover so I can see the image, and there should be some lower elevation rainfall. I was a little worried this step would take me a long time, but I was lucky. Using Mammoth Mountain Ski Patrol's storm summary data, which is available on their website, I found a small storm in March of 2020 that had a little rain. I wanted to use a small storm to minimize the chance of cloud cover obscuring the image. I then wrote some code to filter Landsat imagery based on dates, path, and row, and found that 2 flybys bracketed this storm. The last 9 weeks of my quarter and project can kind of be summed up by these 45 lines of code. It took me a long time, but I am fairly confident that this code and variations of it can estimate the elevation of the snowline anywhere in the western US or Alaska from March of 1984 to present day using Landsat 4-8 data. I'll go into each block of code a little more in depth separately, but the only parameters that need to be changed is where the map is centered on line 4, the maximum elevation of the region you are working in, what image you want loaded in, line 8, and where is your region of interest and how big is your buffer, line 25. Working in Google Earth Engine is advantageous in this regard because instead of downloading individual SRTM tiles from USGS Earth Explorer, you write 5 simple lines of code and you have a DEM for the entire planet, provided the area you're working in is south of Greenland and north of Antarctica. After loading my DEM, I downloaded Landsat Fractional Snow-Covered Area from USGS Earth Explorer. Snow cover is spatially and temporally variable and is concentrated in remote regions, making remote sensing the best approach to measure and monitor snow cover change. The acquisition rate of Landsat limits analysis of short-term snow cover variations, but long-term changes in snow cover duration and persistence can be detected. Landsat Fractional Snow-Covered Area, FSCA for short, provides per pixel fractional snow cover maps that indicate the percentage of a pixel covered by snow for Landsat 4-8 data. The valid range for these fractions is between 0 and 1. 0 is not snow, 1 is definitely snow. This is the FSCA for March 4th overlaid on the DEM, and to the right is the FSCA for March 20th overlaid on the DEM. Next, I set regions of interest along the visual snowline in order to make a histogram. I probably could have done this step a little bit more efficiently if I had more experience coding and working in Google Earth Engine, But my quick and dirty version was to set regions of interest based on latitude and longitude with a large enough buffer to encompass the entirety of the western edge. This process is visualized here. For the March 20th FSCA, this was accomplished in 3 regions of interest, but it took 5 ROIs to cover the higher elevation snow line of March 4th. For the purpose of brevity and presentability, we will only be taking a look at the region of interest centered over the Tuolumne River Basin. These are ROIs clipped from their original FSCAs. As you can see, the snow line has moved down in elevation. On March 4th, it was well above fish camp, whereas on March 20th, it was several hundred meters below fish camp. One cool thing is that you can click anywhere on the map, and the inspector console will tell you if that pixel has snow and what elevation it is. This point is around here. It has an elevation of 1,369. The threshold is telling me that yes, it does have snow, and this layer 3 is saying that yes, it's within the mask. If I clicked somewhere out here, way up high in Yosemite Valley, the output would look something like this. It has a high elevation. Yes, it has snow, but no, layer 3, it is not within my region of interest. And this will be important for the next part. In terms of anything concrete, like what does my project actually do? This is where it's at. You can look at the snow line through imagery and get a spatial understanding, but the objective way of identifying the elevation of the snow line is through statistical analysis. You run the code for your desired region of interest, in this case the Tuolumne River Basin, and the last 15 lines of it gives you a histogram. The top histogram is the ROI prior to the storm, and the bottom histogram is the ROI after the storm on March 20th. The x-axis is elevation, and the y-axis is number of pixels with snow present. To account for random artifacts of snow, I decided that there must be at least 1,500 pixels of snow cover to determine that that is indeed the snow line. Before the storm, it'd be an elevation of around 2,000 meters, whereas after the storm, it'd be an elevation of around 1,300 meters. However, I wasn't really satisfied with these histograms as concrete results, so I downloaded them off Google Earth Engine as CSVs, and I went on YouTube to learn how to make a cumulative distribution function in Excel. So again, before the storm is on top, after the storm is on the bottom. The x-axis is elevation, and the y-axis is probability. These two graphs are the same, just with the maximum y-axis upper bound set to 1%. As you can see, before the storm, 99% of snow cover was at an elevation higher than 2,000 meters. After the storm, 99% of snow cover was at an elevation higher than 1,232 meters. If I were to keep working on this project, one thing that I would want to figure out is how to create a rectangular ROI that encompasses the entire western edge rather than several circular subregions. This would allow me to present the entire snow line on one graph rather than stitching them together. The only thing I really have left to say is that I was disappointed in the visualization of Google Earth Engine. I felt that it was a great tool to do lots of rapid analysis, which is probably what it's intended for with the huge amounts of cloud storage, but I think that ArcEsri products are awesome for actually seeing what's going on. Science is cool, and satellite imagery is really pretty, and Google Earth Engine just doesn't have a symbology tab. This is probably inexperience talking. Coding is great and all, but sometimes you just want to pick the colors on your map without writing it in a crazy syntax. So I downloaded an SRTM tile off Earth Explorer and used the tool raster to tin so I could import the DEM into ArcScene. This is the Tuolumne River Basin with elevation exaggeration set to 3. I then clipped the FSCA for March 4th and 20th to the same area and overlaid it on the DEM. This is the FSCA for March 4th, where 99% of snow cover was at an elevation higher than 2,000 meters. This is the FSCA for March 20th, where 99% of snow cover was at an elevation higher than 1,232 meters. And it wasn't until I did this where it was like, whoa, my snow cover really did increase. Sure, the statistic analysis is great for an objective. My snow line elevation is about 800 meters lower in elevation after the storm, but humans aren't objective, and I do think there's merit in making your signs look cool. Anyways, There are already models that do their best to estimate the elevation of the snow line, but my code is a way of validating those predictions of that rain to snow transition line. And so this code can be used to validate how well the models worked after a storm has passed, anywhere in the western US or Alaska where fractional snow covered area product is available. Thank you to Dr. Fricker for giving me the opportunity to learn how to code.